Hello everyone, welcome to our poster. Today, I'm very excited to share our work, TLMA, Mitigating the Impact of Weakly Labeled Information for Video Anomaly Detection. This work focuses on solving a critical but long overlooked bottleneck in weakly supervised video anomaly detection. As we know, weakly supervised training only utilizes video-level labels, which drastically reduces annotation costs. However, our key insight is that these coarse-grained labels fail to precisely describe the complex content of videos. This mismatch inevitably introduces substantial weakly labeled information, which we define here as WLI. WLI refers to contents whose visual patterns deviate from their assigned video-level labels. In abnormal videos, an abnormal video is uniformly labeled as explosion. However, the actual anomaly only occurs in the foreground of partial segments, as shown in the red box. The remaining transitional segments and background regions are included in the label but are actually normal. In normal videos. On the flip side, all normal videos with diverse behaviors are uniformly labeled as a single normal tag. This single label completely fails to represent the wide range of normal patterns. Consequently, atypical normal segments like those with intense motion or uncommon patterns deviate significantly from typical norm features and constitute another heavy form of WLI. This presence of WLI severely blurs the boundary between normality and abnormality, leading to severe consequences. As shown by the score curves in Figure 2, existing mill-based state-of-the-art methods frequently mistake these WLI segments for anomalies. In A completely normal scene with intense motion is misclassified as an anomaly, and in B, the normal transitional segments preceding an explosion also trigger massive false alarms. Since increasing fine-grained annotations is practically infeasible due to the extreme costs, effectively distinguishing WLI from true abnormal cues is crucial to mitigate misclassifications. This strongly motivates our proposed framework. We propose TLMA, a framework integrating triplet learning and motion-aware enhancement to mitigate WLI interference. Triplet learning strategy constructs triplets using WLI proxies, anchors and positives, and true anomalies, the negatives, to explicitly separate WLI from real abnormal cues in the feature space. Motion-aware feature enhancement module captures interframe edge variations to emphasize motion-salient regions, adaptively enhancing dynamic foreground features while suppressing static background noise. Since anomalies typically happen in dynamic regions, we designed this module to filter out static background noise. Specifically, it captures interframe edge variations using Sobel filters to directly emphasize motion-salient regions. Instead of treating all video tokens equally, the MA module adaptively enhances dynamic foreground features while successfully suppressing irrelevant static background noise. This ensures that the downstream network receives highly discriminative features that naturally peak at actual dynamic movements. With these enhanced features, our second and most core pillar comes into play, the triplet learning strategy. To explicitly eliminate WLI interference, we pull WLI segments away from true anomalies in the latent feature space. We dynamically construct triplets using the anomaly scores predicted by the model itself. We select high anomaly scoring segments from normal videos. Since they are from normal videos but scored highly, they serve as a perfect proxy for atypical WLI. We select low anomaly scoring segments from abnormal videos. These are highly likely to be the normal background parts of those videos. We select high anomaly scoring segments from abnormal videos, which reflect the truly anomalous content. Here is the beauty of our strategy. Both anchors and positives are actual WLI segments. By optimizing our dynamic margin-based triplet loss, we forced the model to pull these WLI segments together in the feature space, while explicitly maximizing their projection distance away from the true negative anomalies. Combined with the standard mill ranking loss, our joint loss collaboratively refines the decision boundary, mapping WLI safely back into the normal distribution. We validated TLMA on 3 major benchmarks: UCF crime, XD violence, and MZD. As you can see from our tables, TLMA consistently delivers state-of-the-art performance. For instance, we achieved an 89.47% AUC on UCF crime and an 86.78% AP on XD violence, drastically reducing the false alarm rates compared to previous MIL baselines. To better illustrate how our framework actually works in practice, let's look at some qualitative visualizations. This figure visualizes our motion-aware module. It clearly shows that our motion map successfully highlights dynamic foreground regions while suppressing static background noise. And this figure compares our anomaly scores with the baseline. Our TLMA yields a much sharper, temporally precise response with significantly fewer false positives caused by WLI. In conclusion, TLMA effectively mitigates WLI impact by enhancing motion features and triplet learning strategy, providing a cost-effective and highly precise solution for video anomaly detection. Thank you so much for your time, and I'd be happy to discuss any questions you might have.